IBC applications. Learn how to configure your application to use IBC and send data packets to other chains. This document serves as a guide for developers who want to write their own inter-blockchain communication protocol, IBC, applications for custom use cases. Due to the modular design of the IBC protocol, IBC application developers do not need to concern themselves with the low-level details of clients, connections, and proof verification. Nevertheless, a brief explanation of the lower levels of the stack is given so that application developers may have a high-level understanding of the IBC protocol. Then the document goes into detail on the abstraction layer most relevant for application developers, channels and ports, and describes how to define your own custom packets and IBC module callbacks. To have your module interact over IBC, you must bind to a port, define your own packet data and acknowledgement structs, as well as how to decode them, and implement the IBC module interface. Below is a more detailed explanation of how to write an IBC application module correctly. Create a custom IBC application module. Implement IBC module interface and callbacks. The Cosmos SDK expects all IBC modules to implement the IBC module interface. Opens new window. This interface contains all of the callbacks IBC expects modules to implement. This section will describe the callbacks that are called during channel handshake execution. Here are the channel handshake callbacks that modules are expected to implement. The channel closing handshake will also invoke module callbacks that can return errors to abort the closing handshake. Closing a channel is a two-step handshake. The initiating chain calls chain close init and the finalizing chain calls chain close confirm. Channel handshake version and negotiation. Application modules are expected to verify versioning used during the channel handshake procedure. Chan open init callback should verify that the MSG chan open init version is valid. Chan open try callback should construct the application version used for both channel ends. If no application version can be constructed, it must return an error. Chan open callback should verify that the MSG chan open counterparty version is valid and supported. IBC expects application modules to perform application version negotiation in on-chan open try. The negotiated version must be returned to core IBC. If the version cannot be negotiated, an error should be returned. Versions must be strings but can implement any versioning structure. If your application plans to have linear releases, then semantic versioning is recommended. If your application plans to release various features in between major releases, then it is advised to use the same versioning scheme as IBC. This versioning scheme specifies a version identifier and compatible feature set with that identifier. Valid version selection includes selecting a compatible version identifier with a subset of features supported by your application for that version. The struct is used for this scheme can be found in 03 connection types. Since the version type is a string, applications have the ability to do simple version verification via string matching, or they can use the already implemented versioning system and pass the proto-encoded version into each handshake call as necessary. IX 20 currently implements basic string matching with a single supported version. Bind ports. Currently, ports must be bound on app initialization. A module may bind to ports in its genesis like so. Custom packets. Modules connected by a channel must agree on what application data they are sending over the channel, as well as how they will encode-decode it. This process is not specified by IBC, as it is up to each application module to determine how to implement this agreement. However, for most applications this will happen as a version negotiation during the channel handshake. While more complex version negotiation is possible to implement inside the channel opening handshake, a very simple version negotiation is implemented in the IBC transfer module opens new window. Thus, a module must define its custom packet data structure, along with a well-defined way to encode and decode it to and from byte. Then a module must encode its packet data before sending it through IBC. A module receiving a packet must decode the packet data into a structure it expects so that it can act on it. Packet flow handling. Just as IBC expected modules to implement callbacks for channel handshakes, IBC also expects modules to implement callbacks for handling the packet flow through a channel. Once a module A and module B are connected to each other, relayers can start relaying packets and acknowledgements back and forth on the channel. Briefly, a successful packet flow works as follows. Module A sends a packet through the IBC module. The packet is received by Module B. If Module B writes an acknowledgement of the packet, then Module A will process the acknowledgement. If the packet is not successfully received before the timeout, then Module A processes the packet's timeout. Sending packets. Modules do not send packets through callbacks, since the modules initiate the action of sending packets to the IBC module, as opposed to other parts of the packet flow where MSGs sent to the IBC module must trigger execution on the port-bound module through the use of callbacks. Thus, to send a packet, a module simply needs to call send packet on the IBC channel keeper. In order to prevent modules from sending packets on channels they do not own, IBC expects modules to pass in the correct channel capability for the packet source channel, receiving packets. To handle receiving packets, the module must implement the onRecv packet callback. This gets invoked by the IBC module after the packet has been proved valid and correctly processed by the IBC keepers. Thus, the onRecv packet callback only needs to worry about making the appropriate state changes given the packet data without worrying about whether the packet is valid or not. Modules may return to the IBC handler an acknowledgement which implements the acknowledgement interface. The IBC handler will then commit this acknowledgement of the packet so that a relayer may relay the acknowledgement back to the sender module. The state changes that occurred during this callback will only be written if the acknowledgement was successful as indicated by the success function of the acknowledgement. If the acknowledgement returned is nil, indicating that an asynchronous process is occurring. Note: applications which process asynchronous acknowledgements must handle reverting state changes when appropriate. Any state changes that occurred during the onRecv packet callback will be written for asynchronous acknowledgements. Modules may commit an acknowledgement upon receiving and processing a packet in the case of synchronous packet processing. In the case where a packet is processed at some later point after the packet has been received, asynchronous execution. The acknowledgement will be written once the packet has been processed by the application, which may be well after the packet receipt. Note: most blockchain modules will want to use the synchronous execution model, in which the module processes and writes the acknowledgement for a packet as soon as it has been received from the IBC module. This acknowledgement can then be relayed back to the original sender chain, which can take action depending on the contents of the acknowledgement. Just as packet data was opaque to IBC, acknowledgements are similarly opaque. Modules must pass and receive acknowledgements with the IBC modules as byte strings. Thus, modules must agree on how to encode-decode acknowledgements. The process of creating an acknowledgement struct along with encoding and decoding it is very similar to the packet data example above. IX04 opens new window, specifies a recommended format for acknowledgements. This acknowledgement type can be imported from channel types opens new window. While modules may choose arbitrary acknowledgement structs, a default acknowledgement types is provided by IBC. Here opens new window. acknowledging packets. After a module writes an acknowledgement, a relayer can relay back the acknowledgement to the sender module. The sender module can then process the acknowledgement using the onAcknowledgement packet callback. The contents of the acknowledgement is entirely up to the modules on the channel, just like the packet data. However, it may often contain information on whether the packet was successfully processed, along with some additional data that could be useful for remediation if the packet processing failed. Since the modules are responsible for agreeing on an encoding-decoding standard for packet data and acknowledgements, IBC will pass in the acknowledgements as byte to this callback. The callback is responsible for decoding the acknowledgement and processing it. Timeout packets. If the timeout for a packet is reached before the packet is successfully received, or the counterparty channel end is closed before the packet is successfully received, then the receiving chain can no longer process it. Thus, the sending chain must process the timeout using onTimeout packet to handle this situation. Again, the IBC module will verify that the timeout is indeed valid, so our module only needs to implement the state machine logic for what to do once a timeout is reached and the packet can no longer be received. As mentioned above, modules must implement the IBC module interface, which contains both channel handshake callbacks and packet handling callbacks. The concrete implementation of this interface must be registered with the module name as a route on the IBC router. Working example. For a real working example of an IBC application, you can look through the IBC transfer module, which implements everything discussed above. Here are the useful parts of the module to look at.